It was Claude Shannon who founded the field of information theory and also invented the entropy of information, Shannon entropy. Shannon entropy can be thought of as the amount of hidden information in a system, or more precisely, the amount of information we can hope to gain by making a measurement of the system. If all the particles are bunched up in the corner, then measuring their exact positions gets you some information, but if you measure the positions when they're spread through the room, you increase your information by a lot more.
So how do these these clouds become charged? Well, to do that, we have to think about some of these atmospheric electricity parameters a bit more. So we have to consider what's called conductivity. So conductivity is the ability of the air for a current to flow in the air. And it depends on this ionization from our cosmic rays and from our radioactivity. So these tiny little ions that are created in a cloud, they become attached to the droplets. And that means that the conductivity goes down when you have a cloud layer. So this is our cloud layer. We're going up through a cloud layer. So our conductivity decreases, is low in the cloud, and it increases when we get above the cloud. If we go to Ohm's law, which if you remember back to your school days, you probably did this in the form of V equals IR. It's basically the same equation, just written in a different way. And that says if you have a current, so in this case, JC, it's flowing through the cloud, and you have a conductivity or resistance, basically the inverse, then if you have an electric field, then the conductivity and the electric field are inversely related if the current stays the same. So because we have a conductivity decrease, we must have an electric field increase in the cloud. And if we take another relatively simple law of electrostatics, so Poisson's equation, that says if you have a gradient in electric field, then you will create a charge, a space charge, rho. So you see that there's a gradient in the electric field on the bottom edge of the cloud and on the top edge of the cloud. So that means that we should get a charge, rho. And that's what we see here. So this is our charge density. So because of the direction of the field and the current flow, we should get negative charge at the base of the cloud and positive charge at the top. And if we manipulate these equations a little bit more, this charge depends on a few things. It depends on the conduction current, so our JC, which depends on the global circuit and therefore the thunderstorms. It depends on the conductivity, which depends on the ionization from the cosmic rays. And it depends on the gradient of the conductivity, which is this bit here, which depends on the height of the cloud, but also the cloud droplet properties. So if we have a really sharp cloud edge, we should see more charge than if we have a woolly one, if you like. So that's what theory predicts. So our theory predicts that cloud edges are charged and that the charge should be transferred to the cloud droplets. So what does this charging of droplets do? Well, we'll discuss this in a bit more detail shortly, but basically it affects the microphysical interactions between aerosol particles and droplets. And collisions and coalescence, which is something that's particularly important in clouds, is affected by charge. So this means that things like the lifetime of the droplets, how long they last, and how they grow can be affected by charge. And many of you will know that it's these small-scale cloud microphysical processes that determine the large-scale properties of the cloud, such as the height of the cloud, its opacity, or how much its reflectivity, basically, how long the cloud lasts, and even the rainfall. That's just one cloud. We've since done many more. I said 30 flights here. We've probably got more than that now. I've basically done this all over the world. I've done it in Antarctica. I've done it in the Arctic, Iceland. I think that's supposed to be Portugal. And if you take the average, I should say that the charge in clouds is highly variable. All of these clouds are charged, just in different degrees of magnitude. But if you take them all together, then what you see is something like this. So the bases are generally negatively charged and the tops are positively charged. And we get about 40 picocoulombs per cubic meter. So that probably means nothing to you. What does that mean in terms of the droplet charges, right? That's what we're interested in here. How charged are these droplets? So if we take the measurements from the optical sensor and the charge sensor and put them together, and we assume that the charge is equally distributed between all sizes of droplets, then we can plot these distributions of droplet charges for the cloud base and for the cloud top. And you see that the median of these distributions is not large. It's on the order of a few electrons, which doesn't sound like much, but believe it or not, it is actually enough to influence some microphysical processes. But the interesting thing is the tails of these distributions. You can see here that there are some droplets that have hundreds of charges. And I should point out that the charge sensor is saturated in a lot of these clouds. So I think these charges are actually quite a bit more than what they are here. So that brings us on to, well, what does that level of charge, what effect does that have on the droplet behavior? So here I'm going to talk about some, I guess, theoretical considerations as to how charge can affect cloud microphysics. So the first one is the diffusive growth of droplets. So droplets can grow via condensation and they can shrink via evaporation. And you find that the surface tension of, basically charge can affect the surface tension of the droplets, which means that they will be more likely to form at lower critical supersaturations than if they're not charged. So if you look at Kohler curves and things like this, then you can work this out theoretically. And so what you find is that if the droplets, so the charge on the droplets is increasing in this direction, if you charge the droplets, then they form at lower critical supersaturations than if they're uncharged. And when they do form, they're larger droplets than what they would be if they're not charged. So this suggests that condensation and evaporation can be affected by this process, by charge. The other process that might be affected is collisional growth. So this is the other way that, well, probably the way that you think about cloud droplets growing in a cloud. It's by colliding with each other and sticking together. And that's described in terms of the collision efficiency. So the idea here is you've got one droplet and then you've got another one, and as it comes close to it, it can be influenced by the electrostatic force. And so if it's charged, then it's more likely to stick to that other droplet, and therefore they grow. And the reason this can happen is because of something called the electrical image force. So if you've got oppositely charged droplets, it's probably fairly obvious that they can attract each other. But everybody probably remembers from school that if you've got the same charged droplets, if you've got two positively charged droplets, we were all taught that Coulomb's law of repulsion means that they will repel each other. And that's true. But if you've got droplets, then it's different because the charge and the droplets can move. So Coulomb's law is for point charges, where the charges don't move. But droplets have charges that can move. So the idea is if you've got two positively charged droplets, they will each induce a negative charge in the other drop. And so this is actually attractive. It's only valid at small, short-range forces, but it does certainly theoretically have an effect on how droplets how they can collide with each other. And it tends to be, it's a larger effect for small droplets, so typically droplets that are smaller than 10 microns. So this is showing that for the smallest droplet sizes here, as we increase the charge, the collision efficiency gets larger. So these are the two ways that we think that charge might affect cloud microphysics. So one of the large-scale clouds processes that we can model, and we've started to do this now, is rainfall and what the effect of charge has on rainfall. So this plot here is modeling the time that it takes for droplets to grow to a size where they're raindrops. They're big enough to be raindrops, so that's about 500 microns. And if you add charge into this, what you find is that the drops reach raindrop size quicker if they're charged than if they're uncharged. And it's not a huge amount faster, but it is faster. And so this is a huge interest in parts of the world where there's a water scarcity issue. So we've had some funding recently from the UAE, the United Arab Emirates, they're very worried about water. They have a water shortage and they have an operational cloud seeding program. So this is their aircraft where they emit salt particles into clouds to try and help the droplets grow to produce rain. So we've had quite a big project funded to try and look at whether charge can influence rainfall. And one of the things that's happening right now is we've made these ionizers to basically charge the cloud droplets. So instead of emitting particles into clouds, which isn't a very sort of efficient, or it's not a very clean way of doing things. Some places they use silver iodide, at least here it's just salt. But the idea is if you can charge the droplets, you're not emitting anything that's not there already. And theoretically, that should have an effect. So this is actually going on right now. They're flying this on their operational seeding aircraft. And I could spend all night talking about that as well, but I won't. So if you're interested, ask me about that later.